In the context of graph theory, the concept of path validity is crucial, particularly in the valid path-based graph vertex numbering problem. A graph G of order n is assigned a numbering π, a bijective mapping from its vertex set V, G, to 1, 2, n. A two-path in a numbered graph is considered valid if the middle vertex's number is strictly smaller than its endpoints. The validity of π, denoted as php, G, is the quantity of valid two paths induced by π. The minimum and maximum validity of G, phi min, G, and phi max, G, respectively, are the minimum and maximum of php, G, over all possible numberings π. The valid path problem has implications in various applications, including enumerating chordless cycles in graphs, predicting nuclear magnetic resonance chemical shift values, and modeling discrete systems. An example of the 4x4 grid graph with three different numberings illustrates the significant variation in valid paths depending on the graph structure and numbering used. The minimum and maximum validity of a graph can vary greatly, and it is conjectured that the valid path problem is n-fard, requiring a specific numbering for each graph class. The paper delves into the minimum and maximum possible number of valid paths in different graph classes, including paths, trees, cycles, wheels, and complete bipartite graphs. Detailed proofs and mathematical derivations are provided for each graph class, highlighting key points and lemmas that support the main arguments. The authors analyze the properties and behaviors of these graph classes under the valid path-based numbering framework, offering a comprehensive exploration of the subject. Here is a combined summary of the 4 pages, covering all major points, and following the guidelines. The paper explores the concept of valid path-based graph vertex numbering, focusing on complete bipartite graphs, complete graphs, and planar graphs, particularly maximal planar graphs, MPGs. For complete bipartite graphs Kp, Q, the minimum number of valid paths is given by the equation phi min, Kp, Q, equals 1/6, 3q1, p squared p, as illustrated in Figure 2b. For complete graphs Kane, the minimum number of valid paths is given by phi min, Kane, equals 1/6, n-33n squared plus 2n. The paper then shifts its focus to MPGs, citing the Hakimi-Schmeichel theorem, which states that if G is an MPG with more than 5 vertices, then 2n4 is less than or equal to tau, G, is less than or equal to 3n8, where tau, G, represents the number of triangles in G corollary 2. By-Helden further elaborates on this theorem, stating that 0 is less than or equal to sigma, G, is less than or equal to n4, where sigma, G, represents the number of separating triangles in G. The authors also discuss Apollonian graphs, a subset of MPGs, and present a lemma stating that if n is an Apollonian graph of finite order n, then the minimum number of valid paths is 6. Furthermore, they prove that the minimum number of valid paths in an Apollonian graph of order n is 3n8, and provide a specific numbering algorithm to achieve this minimum. The maximum number of valid paths in an Apollonian graph is shown to depend on whether n is even or odd, with distinct formulas for each case. For even n, the maximum number of valid paths is given by n-27n, 2 plus 2, while for odd n, it is given by 4, n-2/4, 3, n, 2, plus 2. These results are demonstrated through examples of maximal numberings of P2Pn2 graphs and Q2, n2 graphs. The research discusses the validity of path-based graph vertex numbering for specific types of graphs, particularly for Apollonian graphs of the form P2 times Pn-2. It presents proofs for the minimal and maximal quantities of valid paths in such graphs, which are crucial for understanding their structure and properties. The authors demonstrate that when anise of the form P2 times Pn-2, it is maximal in the sense that a numbering of it can be found that induces the maximum quantity of valid paths among all numberings of all Apollonian graphs of order n. This is achieved by leveraging the properties of these graphs, including their even or odd nature, to construct minimal and maximal numberings. The results are illustrated through various figures, showcasing examples of suboptimal numberings and counterexamples that highlight the limitations of these lemmas. The research contributes significantly to the understanding of graph theory and its applications, particularly in the context of Apollonian graphs.